Hello and welcome to another one of my videos. This video, as the title implies, will be about electromagnetic interference in relation to multicopters. Is it made up, or is it something real that can cause serious problems? I will be trying to explain this phenomenon as simple as possible so everybody can understand the basic principle of electromagnetic interference. This means simplify terminology, skip the nasty calculations and keep it practical. Okay, now that we have that out of the way, we can start with the question, what is electromagnetic interference? There are different definitions available on the internet depending on the application. But for this video, electromagnetic interference is the unwanted result of one conductor inducing energy into another conductor. In this video I will be using an oscilloscope to show the results of some experiments. To better understand the results, I will first explain the workings of an oscilloscope. An oscilloscope visualizes the voltage at a certain time. It will plot the voltage points along the horizontal axis, and the vertical axis represents the measured voltage at that specific moment in time. So when I connect the input of the oscilloscope to a blinking LED, we can see the voltage rise and fall over time. The middle line in this case, and during all the other examples that I will show you, represents 0 volt. And here we can see the plus 5 volt when the LED is on. In the bottom left corner, the voltage per division is shown. In this case, it is set to 2 volts. This means that every vertical block represents 2 volts. And as you can see, there is some voltage drop in the USB cable that I use. The input impedance of the oscilloscope is very high. In my case, it's 1 megaohm with 100 picofarad capacitance. In layman terms, it means that the resistance is very high and that there is almost no current flowing through the probe of the oscilloscope. So we only measure the voltage difference. Okay, let's start with a single conductor or wire. When a current flows through a conductor, a magnetic field is formed around the conductor. In this case, you could think of an electromagnet like this. It's just a piece of wire wrapped around a nail. When a current flows through the wire, it creates a magnetic field that makes it possible to pick up metal items like this nut. And when the power supply is disconnected, the magnetic field disappears and the object is released instantly. And the opposite is also true. When a wire is placed inside a changing magnetic field, it is possible to generate energy. Think of it as a generator that charges the car battery. Now, a single wire does not produce enough energy for this test. Therefore, I made this 5-turn coil around a plastic tube. The ends of the wire are connected to the probe of my oscilloscope. In the tip of this pen, there are magnets. This makes it easier to move them through the coil. These magnets, by the way, are way stronger than the electromagnet that I just showed. By changing the magnetic field, I can induce an electromotive force, or abbreviated EMF, into the wire. Depending on the resistance of the circuit, the electromotive force will create a voltage or a current. Because the input impedance or simplified resistance of the oscilloscope is very high, we will see a voltage change instead of a current. First, I will manually change the magnetic field in the coil. As you can see on the oscilloscope, the voltage difference produced by the changing magnetic field is only a few millivolts. To change the magnetic field faster, I will drop the magnets through the coil. Watch the screen of the oscilloscope and see what happens. Okay, now let me zoom in on that voltage spike that we see. So by dropping these magnets, the change of the magnetic field is faster and the voltage difference is significantly higher, in this case 30 millivolts. Now let's combine these two tests. Here you can see the electromagnet inside the coil, and again the wires of the coil are connected to the oscilloscope. For this test I resized the voltage per division from 5 millivolts to 200 millivolts. Now the electromagnet is not as strong as the magnets that were inside the pen, but the change of the magnetic field will be much faster. Now watch what happens when I connect the electromagnet to the power supply. You can see the voltage spike that is produced by the induced EMF. Now note that there is only a voltage difference when I connect or disconnect the power supply. Only at that moment the magnetic field inside the coil changes. When the power supply is connected constantly, there is also a constant magnetic field. Now let's summarize what we've learned before we get into some more practical examples. A changing magnetic field induces an electromotive force, or EMF, in a conductor that is inside this magnetic field. More EMF is induced when the conductor is longer, while the change of the magnetic field stays the same. Faster changes of the magnetic field induce more EMF. Stronger magnetic fields also induce more EMF. And now we understand the Faraday's Lenz's law. It states that the induced electromotive force, or EMF, is the result of the change in the magnetic field times the surface area of the conductor inside this field divided by the time it takes to change the field, multiplied with the number of windings and place a negative sign to be mathematical correct. In short, if you want to minimize the induction of EMF, you don't want any long wires in close proximity of high current wires that produce fast changing magnetic fields. And you guessed it, a multicopter is one of the worst places that you can think of. High current motors can be controlled with 20 kHz pulses, and the batteries can deliver peak currents up to 100 amps without any problems. So what does this mean in real life? To answer that question, I'm going to use this test setup. In this test setup, I have a LiPo battery, an electronic speed controller and a 1200 kV motor with an 8-inch prop. I can change the speed of the motor with this potentiometer. I will now exchange the coil with this short piece of wire. During a constant RPM of the motor, I can now probe the electromagnetic field from the motor wires up to the battery. Now let's see what happens. Fascinating results, aren't they? In the next video, I will explain the results of this test and what this means for the electromagnetic interference in relation to a multicopter. Thank you for watching and see you next time.